In this session, you will be learning about solar panels.
Solar panels, also called photovoltaic modules, are made up of individual solar cells.
Each solar cell converts light into electricity and heat. When placing solar panels in series, this is in order to gain a specific voltage. A series of solar panels is called a string. When you put multiple strings in parallel with each other, you create an array. An array is helpful to produce a specific current. In order for electricity to be generated, solar cells must be able to efficiently use the photoelectric effect. In 1921, Albert Einstein was awarded the Nobel Prize in Physics for the photoelectric effect. The photoelectric effect is the ability to emit electrons when in contact with light. What happens is when certain materials are bombarded by light, the loose electrons are given kinetic energy and jump off the material. Kinetic energy is half the mass multiplied by the velocity squared. The higher the amplitude of the light wave, the more kinetic energy the electrons will have. You could think of these interactions as waves of different height or amplitude hitting beach balls off the dock. The higher the wave, the faster the balls will move. A solar cell is made up of multiple layers of material. On the top is a glass cover and anti-reflective coating to protect the cell from damage. Behind the cover is the front contact grid used as the negative terminal of the circuit. Next is the N-type silicon with a semiconductor with excess electrons. Under this layer is the P-type semiconductor, of which contains free holes or the absence of electrons. Lastly, the bottom layer is the back contact, which is used as the positive terminal of the circuit. Due to this action, electric field forms within the cell and creates a current. The three main factors that play a role in achieving the most power from a solar panel is temperature, amount of sunlight, and load resistance. We will start with temperature. Looking at the graph on the left, you can see the power is greatest with colder temperatures. Why is this? Well, both heat and light vibrate electrons, and because the potential difference between the excited and resting electrons is smaller due to the increased heat, there is a decrease in power. Now for the other two, let's look at the graph on the right. As you can see, there is a specific voltage and current that generates the most power. The current depends mainly on how much light is hitting the solar panel, and thus, if the sunlight is constant, it should remain close to the same. Voltage, however, depends on the load resistance and temperature. The load resistance is essentially the total resistance of the components in the connected circuit. In order to generate the most power, a solar panel should be at low temperature, in direct sunlight, and the correct load resistance. In this activity, you will be able to find where the max power point is for your solar panel. You will achieve this by drawing a graph of power versus voltage. The circuit on the left is what you will be building. You are going to use the device on the right to record the current and voltage for every resistor you use. Each resistor will be a new point on your graph. As you can see, the device has a positive prong in red and a negative prong in black. You will be touching the red prong to the circuit between the positive terminal of the solar panel and resistor for finding both the voltage and current. When measuring voltage, the black prong will touch between the negative terminal of the solar panel and the resistor. Lastly, in order to find the current, all you have to do is move the black prong to touch the wire between the red prong and the resistor. Okay, in this video I'll be demonstrating how to use a multimeter in finding what resistor should be used with this type of solar panel. We'll find out which resistor generates the most power. So, we need some resistors. I have a box filled with them, but just have a wide range of resistors that you can use to find. A multimeter that finds the voltage and current, the solar panel that we'll be putting on the device, the breadboard we've been using, some alligator cables. You don't specifically need these, but they help with attaching them to the solar panel here. And a couple wires. And of course, some paper so we can graph the voltage and power, and a calculator. So let's begin. We'll be adding the alligator clips to the solar panel. The white is going to be ground, so we have black to go with that. And then red for power, which is the same color. Now we can add our wires. We'll create a power strip here and a ground strip here. We'll add these there and there. All right. So let's just test this out to see how much voltage is actually in the solar panel right now. So lift these up. And let's push this aside so I can show you how to use a multimeter. Okay. So when finding voltage, we're going to put it in parallel when we're doing this. We're going to be using a resistor, but I'm just showing you how to do it right now. The black should be in COM. And for this, we're only going to be in this place. We're never going to do the 10 amps DC right here. This might actually, if we use it, we might actually blow the multimeter. So keep it where just these ports. And we're going to be using the voltage here, current here, and resistance here. So let's try find the voltage. And what these numbers show is the range. So if there's a voltage that you think is going to be less than 20, put it here. If it's going to be more than 20, up it up here. This is going to be how high it would be. So I don't think there's going to be more than 20, and I think it's going to be more than 2,000 millivolts. So I'm going to put it right here. So now let's bring this over. Let's test it out. So this is kind of tricky. And it's reading 6.03 volts. So when dealing with this, make sure the solar panel is in the same amount of light so we catch accurate readings. So just try to keep it stationary while doing this. So now let's add a resistor. Let's try, so I have a bag full of these. I don't know which one this one is, but we can test it out with our multimeter. So move those out. So we can put our resistor on two separate different rows, not on the same one. And then we're going to put it in parallel with it and have it set to, let's see what we should do it now. Let's try it here. Let's see what we get. So we get a decimal. That means it needs to be changed to a different value. It's a little, there we go. Okay, let's keep it steady. So we're getting like 270 ohms for the resistor. Now let's add it. We're going to just move this here. Move this here. Now there's a complete circuit going through all the way here to ground. So now, to find voltage, we put it in parallel with it. So let's move it to 20 for the max and see what we get. We get 1.59 volts. Okay? So what we could do is, on a piece of paper, let's write the voltage, current, and resistance that we'll be having. So move this away. So let's have this voltage. And you could do this with as many resistors as you want. I'm going to be doing about like 5, but the more you do, the more accurate you'll be getting. The best is to have a wide variety of resistor values. So here, so we had, what was it, 270 ohm. And the voltage was, let's check again. Did a little change on us, 1 sec. 2.24, we'll say, for the voltage. So we have that so far. And we can calculate current now with V equals IR. So we get, what is this? 8 milliamps, but it's 0.083 amps. So you can leave it as that, but we're going to test out every current to make sure we have correct readings. So now let's go to current and find a value. We'll try this first. We'll have a... Now the difference when finding the current is that you have to do it in series instead of parallel. So what we're going to do is have this go there. Now we're going to be adding the prongs here and connect it to the resistor. Now it has to flow through it. There's no other way to get to here other than through these. There's no actual connection yet. We're going to supply the connection through here and create a pathway. So let's try this. Actually, I'm going to put it somewhere else that's easier for me to hold on to. Okay. So we get 8.2 milliamps. Okay, that's exactly what we got. So we did good readings right there. All right, let's do another resistor. Let's see. Let's do one. So we had 270 ohm. Let's do something a little bigger now. What's this one? It's a little bit smaller than that. Let's try... Yeah, let's try this one. Okay. We have between 2.2 kiloohms and 3.9. So we'll see which one we get. In order to find the resistance of a resistor, we can either use the multimeter or you can use color code table where you can find online. So let's take this out and add it to our circuit. Make sure it's the same light. Now let's find the voltage. Change it to 20. And, oh, other way around. Let's see what we get. Okay. So we get 5.95 volts. So we can add it there. Volts. And let's see what resistor we have here. So take it out of the circuit, change it to, we'll say there. So that's a decimal. So we can go a little bit higher. Actually, no, it was a little lower. Let's see. Oh, I guess I was right there. Okay. So that means, because we're on the range of 20 kiloohms here, that means that's the highest it will be. So we're going to be actually in kiloohms. So what this reading says, we have 3.88. Well, that means that we have a 3.88 kiloohm resistor, which is probably what we have in there. So 0.88 kiloohm. Now let's calculate the current. We get 0.00153 amps, which is 1.5 milliamps. And now let's check if that's correct by, let's see, putting that there. Now let's connect it in series. All right, change it to, what should we say? We'll try 20 milliamps. So I'll connect it here, here. So, yep, that's right. 1.543 milliamps, which is what we got here. So we're getting accurate readings. Okay, let's do 3 more. Let's try something a lot higher this time. Move this over, go through some. Okay, this should be good. All right, put that out. And let's pick this one. Okay. Connected on 2 different rows, not on the same circuit. Now let's change it to, I think it's going to be a lot. I think it's going to be over 200 kiloohms, so let's try that. And I was correct. So what we have, because we have 2,000 kiloohms as a max, and it's in this range, that means whatever number is going to be in kiloohms. So if we see 561, that means we have, this resistor is 561 kiloohms. So let's write that down. Ohms. All right, so let's find the voltage and current now. So add this back into our circuit. Change it to 20 and put it in parallel. So we are getting 6.06 volts. All right. Volts. Let's do some calculations. We get okay. Jeez. This is 0.01 milliamps, this one. So let's actually, yeah, all right. Let's change this to milliamps so it's a little easier. 8.3 milliamps. This one's 1.53 milliamps. So as of right now, the 270 ohm resistors generate the most ampage. But the 561 kilo ohm is generating the most voltage. This is what's going to be, we're going to be using to find the most power, because these are going to be altering. You have to find a specific point where the voltage and current is going to be generating the most power. So let's check if our calculation is correct and find the current of this resistor. All right. Take this out. So there's only one pathway to go. Put this on to 20 milliamps. And let's connect the multimeter in series. Okay, let's see if we can actually get it. Oh, let's try this one. Okay. And that's 11 microamps. And yep, that's exactly what we got. It's just converting units, so that's exactly what we got. So we're good. All right. Let's see if we can do something in between 3.8 kiloohms and 561. Let's try to get one of these. Okay. Okay. This one's going to be, I think it's going to be, what was it? It's going to be a little above, it's going to be below 2,000 kiloohms. So, let's test it out. And we get 118 kiloohms. right. Let's find the voltage and current now. Add it back into our circuit. Change it to 20 volts as the max. And we get 6.05 volts. All right. Do a little calculation. 6.05 divided by 118 kiloohms. You get 0.051 milliamps. All right. Now let's find the current. Let's change it to 20 milliamps. 0.05. Yep, that's exactly what we got. Awesome. Now let's try one more. So we have big resistor in the middle. What should we use? Let's see what we got. We can try a very small resistor. Let's do that. Okay, let's find what resistance this is. Alright, let's change it to, it's not going to be over 200 ohms, so we're going to put that as the max. And let's see what we get. This is, readings are a little wacky. This is because it's a low resistance and it's hard to actually read this. We'll say, oh geez, let's keep it steady. We're going to say 9.2 around. 9.2 amps. All right, now let's find the voltage. We get, wow, it's a small voltage. So we get 47 millivolts. Yeah, because that's a decimal, we should be using this one, which is a little smaller. Yep, we'll say 46 millivolts. Now we can calculate the current. We have a big current. We get, wow. Let's try this reading again, because that's a massive current. So that's 20. Yeah. Yeah, that's all right. Okay. So it is millivolts. All right. Let's try that again then. 0.46 divided by 9.2. Ah, there we go. So we get 5 milliamps. All right, so this is 5 milliamps. That's better. All right. Okay, now we're done with this. Now we're finding which resistor generated the most power from the solar panel. So let's move this out.
Now we'll have this. Now we're just going to make a little graph here of the voltage with the power. And of course, we have V equals IR, B equals IV, right? So let's break this down into 2s, 4, 6. So each one is this 2 volts, 4 volts, 6 volts. And we'll see about the power. All right. Let's see the first one. Actually, let's get another piece of paper here. Let's write down the power for each. All right. So we'll take the first one with the current and voltage. We get, let's see, 2.24 times times. Ah, that's why. Okay. Sorry, my calculator wasn't working that well right there. Okay. So we get 0.01, we'll say 9 milliwatts. Okay. Now it's due for the 3.88 kilo ohm resistor. So we get 5.95 times 1.53 milliamps. I forgot to multiply. There we go. We get 0.009 milliwatts. I'll do it for the 561 kilo ohm resistor. 6 multiplied by 0.011 milliamps. All right. So, actually, doing that in, all right. Milliwatts. Well, let's try the next one. These should be actually in watts. It's not milliwatts. All right. Now, this one, 3.085 10 to the -4 watts. We can change that all to milliwatts afterwards. Let's do our 9.2 ohm resistor. So we have volts times 5. So we get 2.3 times 10 to the -4 watts. Now we'll do power in milliwatts. A little easier. So, yeah, that's just 19 milliwatts. That's just 9 milliwatts. This one's 0.067 milliwatts. This is 0.309 milliwatts. And this last one is going to be 0.23 milliwatts. Okay, so we have our power, and now let's do a little graphing. So we can see that the most power, so actually we can see from now where the most power is getting generated. It's actually from the 270 ohm resistor with 19 milliwatts. As you can see here. So let's do a little graphing. Voltage, and we'll say that this is 20, this is 10, 5. All right, so the first one, we have 2.24 volts, so it should be around here, and we have 19 milliwatts. This is milliwatts. So it'd be right around here, roughly. Then we have the 3.88 kilo ohm resistor with a voltage of 5.95. We get 9 milliwatts. So we'll go to here, it's almost at 6, and we go to around here. All right. Then we'll do the 561 kilo ohm, and we get 0.067 milliwatts. Let's actually do those calculations again, so we're very accurate. Okay, that's right. Okay. So that's 6.06, so it's right above here, and it's barely 1. So we'll say it's right around here. All right. Now our 118 kilo ohm is 0.309 milliwatts. So that's basically kind of the same thing. Just do a little higher. Two very close dots. Now we have the 46 millivolts. So this is far down here with 0.230 milliwatts. So basically, let's say right here. So if we do a little graphing, we'll see that the graph of the solar panel is right here. And the max power point is the resistor 27 ohms.
During this session's construction, you will be creating a 45-degree stand for your solar panel and attaching it to the case. In addition, you will be wiring the positive wire of the solar panel to the VIN positive hole of the current sensor and the negative wire to ground.
In this video, I'll be showing you how to create the stand for your solar panel and adding the solar panel to the circuit we have right here. All right, so now let's first by starting to create the stand for it. So I used galvanized steel, but you could think of anything to use, but you could be creative, maybe other steel, but just something that actually retains its shape, because what I'm going to do now is I'm going to bend it at a 45-degree angle, approximately. Let's see. So you can see there. So anything that can retain its shape like this, just keep it like that, that'll be good. I just use galvanized steel. So we'll be adding it to the case here with our foam double stickies. So let's add 3 to this. Let's do it right there. And here. All right. Now let's peel them off. Okay. Now let's orient it towards the battery, where the battery is. So right here. Can bend it a little bit to make it a little better. Okay, awesome. So secure it on the case. Make sure it's the top of the case that removes, not on the bottom. So now we have that. Now we can add 3 more so we can put our solar panel on it. Okay. Move the stickies. All right. So you can see that the wire is here. We're going to want it to be going through a small hole here. So let's kind of maneuver it this way and just attach it like that. So it's about there. All right. Awesome. Now let's put them through the small hole here. All right, sweet. Now we can take off the lid. And now we'll be adding it to the circuit here. We're gonna be using a battery to power it. We need a screwdriver, some solder, and a soldering iron. So let's start by screwing the power into the current sensor here. So this is unscrewed, so we can just place it inside as best as we can. And then screw it tight. All right, do a little tug to see if it's good. Nice. All right, now the last thing we have to do is have the ground of the solar panel go to the ground on our circuit board here. So let's find some place we can put it. We'll put it in this hole. So move the stuff aside. We don't need that right now. And we'll, awesome. All right, so it's there. Bend it to make it a little easier to solder. Take our soldering iron and solder it onto the circuit board. Awesome. All right. Sweet. So now, if you can see with our LED here, if we allow the solar panel to actually find some light, you should see it actually get brighter. It's very faint, but it does work. You might not be able to see it on the camera, but it's definitely working here. Okay, now we can put the power cable into our Arduino. Try to put everything inside. Oop, this might be a little tricky. Okay, let's see if we can maneuver it. All right, do it like this. That. Right. Doesn't have to be perfect. Just make sure the wires are all intact. Okay. So we have that, and we have the LED that's working inside. Okay, now the last thing is to do, to add our battery. Let's just slide this off. Take your 9-volt battery and put it in there and kind of just push your thumbs in the direction. There, it should snap in. There. And to power it on, just flip the switch. You should see that the green light inside is on, and that's our Arduino. When we turn it off, it should go off. And now it's back on again. So it's working. So now we're able to find the current and voltage at the solar panel.
Your main experiment is figuring out which cardinal direction will enable the solar panel to best fit the demand for power on the power grid. Most solar panels on houses send their energy to the electric company first in order to gain some additional money and other benefits because it could be sent to other people on the grid. The last session will include looking at data provided to you or recording it yourself with your device. But for now, you will be completing the first page of the provided paper. Brainstorm some ideas to which direction you think will be the best and think of information you already know about the sun and power grid. This concludes session 3 of the current solar panel program. I leave you with this quote: "We cannot solve our problems with the same thinking we used when we created them."